the computer audio. Then what? Start video. Daniel's with us.
Hello, good morning, Mr. Griffin.
Oh, Mohammed's with us. Let's see who else we got here. Oops, something bad happened. I think I pushed the wrong button here, guys. Let me try again here. Dang it. Might have to start over again. I don't know what happened. I don't know what I did.
What's wrong?
Well, I want to see the picture of me and the whiteboard here so I can do this. And it's not showing up. I might have to start all over again. I don't know.
What do you see?
Okay, well here. Let me push Zoom again here. Meetings. Thermodynamics, that's what I want. Yeah.
Is that a gallery view
maybe,
versus speaker view
maybe
issue?
I'm back on. I think I'm okay now. I got Nathan here and yeah, things are looking up here now, guys. I've got a good class. I've got Bryce, Alex, Braxton, Brian. Let's see who else I've got here. Nicholas, Taylor, Reagan, William, Chase, and Julian. Got a good class. All right, well, let's get started here. What are we going to do here today? Do you guys have any questions for me?
Can you go over the problem 433?
You want to look at 433. Now, let me see what that is. 433 is it's a compressor, R410A. Mohammed, what do you want to know about it? Everything?
Yeah.
He wants to know everything.
Especially the PV diagram.
Especially the PV diagram. Well, why don't I just do the PV diagram, Mohammed, and then we'll do something else maybe.
Yeah, that'd be fine. I just actually need to do the PV
All right,
diagram.
what I'm doing now is I'm doing 433. It's R410A. I'm going to need that table in the back. So let me find it. R410A. Here goes. I'm looking for it now. Yeah, I found it. Now, I always go to the what I call the vapor dome chart. It's really called the saturated chart. I go there first. And you know it's going to have a vapor dome that always kind of looks like that. And they said it's minus 25. Well, see, minus 25 kind of down in here someplace. So let me draw it. I like to put my isotherms in red. So here's my isotherm. There it is. And it goes near like that, minus 25. Yeah. So we've got the minus 25. And if you look on the table there in the back, this saturation temperature at minus 25 is 329.7 kilopascal. But see, that's not what we have. Yeah, yeah, it is what we have. Because they said X is 1. Well, that means you're right here, see? X is 1. That's the quality. That means you're 100% vapor. That's what that means. So there's state 1. Now the exit is at 1200 kilopascals. Well, you know what? 1200 is bigger than 300. So 1200's 1200 kilopascals is bigger than that. And I'm going to draw an isobar now. I need blue for that. Here's a blue isobar. Dun, 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 dun. Oops, kind of got a kink in it there. If you just tuned in, I'm doing the PV graph for Mohammed for problem 433. And what I just drew is the 1200 kilopascal isobar. We know we're on that isobar because they said so. Read it. It says it exits at 1200 kilopascals and 60 Celsius. Well, 60 Celsius, let me draw that for you. That goes up there kind of towards the top. Here's the 60 Celsius. You are looking at the 60 degrees Celsius isotherm. And here's our process. Here's state 2. Here's state 2, and here's our process. From 1 to 2. There's 1. There's 2. There's your process. There's your arrowhead. And boy, Chuv, we're done. Mohammed, anything else?
No, that's it. Thank you.
Mohammed, are you happy?
Yes, that's okay. Thank you.
Yeah, we're good. Okay. Well, let's see what we're going to do today. He had a question. Anybody else have a comment or question there? Let me see what I'm going to do here today. Okay. Hey, I just did some of your homework for you, didn't I? That's okay. It didn't hurt anything, did it? Now today what we're going to study is, I was thinking of studying condensers and transient processes. Let's go with the condensers first. Now, I hate to do your homework. Let me look here. I don't want to do all of your homework for you. Yeah, that would be bad. Bad to the bone. I want to do a condenser problem. Let me erase this and we're going to do a condenser, okay. Now, a condenser is just a type of heat exchanger. In other words, right now at this moment, we're studying heat exchangers. Come on now, heat exchangers. That doesn't work very good. Let me try a different one. Yeah, that's better. Now, there's a couple of things you need to know about heat exchangers. One is that the heat exchange, there's a heat exchange, all right, but it's internal. They don't exchange heat with the environment. They exchange heat internally, if that makes any sense. And we're going to do problem 459. That doesn't show up. I'll write it over here. We're going to do problem 459 here in a few minutes. But heat exchangers, there's two things you need to know. One of them is that the heat exchange is zero with the environment. All of the heat exchanging is done internally in the heat exchanger, but not with the environment. And the other thing you need to know is heat exchangers are isobaric. They're isobaric devices. Okay, now we're going to do 459, and let me find it here. What page is it on? Let's help me. 459. I think I've got it here. There it is. Okay. Well, let's draw a picture of it. Now, here, this is the device sketch. And let me scoot that over just a tad. Now you've got something coming in here, state 1, and something going out here at state 2. Let me read the problem here. Water, 1 kilogram per second water flows in with quality 95%. Okay. So the way I understand this is you've got an m dot coming in of 1 kilogram per second at 10 kilopascal. And a quality of 95%. And then it comes out at state 2 at 10 kilopascals. Notice it's isobaric. Look, 10 kilopascals coming in, 10 kilopascals coming out. Hey, that's isobaric, isn't it? It's isobaric. But it's saturated liquid. Coming out, it's saturated liquid. That's interesting. Here, let's do the PV diagram. Now we haven't gotten to the cooling water yet. Maybe I should draw that. They've got some cooling water coming in here. And there's these piping tubes like that. And then it comes out. This is cooling water from they call it lake water. It comes from a lake. It's the cooling water. And you know what? It's probably going to warm up. Probably going to warm up. That's what happens to cooling water. It warms up. I don't know what the temperature is. Let me read it here. The cooling done by the lake water at 20 degrees. Yeah, here we go. 20 degrees comes in and it returns to the lake at 30 degrees. It warms up, huh? Okay. All right, well, great. Now let's draw the PV diagram. Here we go. We're dealing with water, and you know water is going to go. There you go. Oh, by the way, they gave these symbols. They said this is state 3, and this is state 4. All right. Okay, help me go to the water table back here. And let's find this state 1 at 10 kilopascals. Go to the saturated chart. Find 10 kilopascals. I found it. You know what? It's way up high in your table, so that means it's way down low in your PV diagram. So you're down here someplace. (10 degrees Celsius). But they said it's got a quality of 95%. Well, that puts you down in here someplace. Here's state 1. You're over here almost to the right side of your diagram. We could get some values there. Why don't we get V1 and maybe, do we know T1? We don't even know T1. We'll get V1, T1, H1. That'll be good for us. Here, I'll get V1. V1 is, we're at 10 kilopascals. To get V1, you got to go like this. You got to go 0.001. 0.01 plus 0.95, 14 point blah, 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 14.67254. Does all that show up on your, yeah, pretty much. Now to find the temperature at state 1, well, it says it's 45.81. It's 45.81 degrees Celsius. Now the H1, we got to use that formula again to get that. The H1 is going to be, maybe I need to scoot that over just a hair here. H1 is going to be 191.81 plus 95 times 2392.82. Now, if anybody had trouble with finding any of that, just speak up, and I'll tell you where it was. It was in table B.1.2. That's where I got these numbers. Now let me get this V1 here. See, this is going to be V1. It's going to be 0.00101 plus 0.95 times 14.67254. Did you get 13.9? I'll round it off to 4. We think we know V1. Now let's get We already got T1. Now wait a minute, I'm getting mixed up now. This is not 10 degrees. Where did I get that 10 degrees from? It's 10 kilopascals. That was wrong. Somebody could have gotten a thank you point for that. This temperature is 45.81 degrees Celsius. Now I think I have it right. I think that's right. There's V1, there's T1, and now we need H1. Okay, well, I'm going to do that now. 191.81 plus 0.95, 2392.82. Now, correct me if I'm wrong on anything, but I'm getting 2464.99, there you go, kilojoules per kilogram. Well, we got state 1. Now let's go to state 2. Any questions so far? Well, I got a question for you. State 2 is at 10 kilopascals, same as state 1, but it's at saturated liquid. Where is saturated liquid? Let me ask somebody. Hey, William, unmute and say hello, William, please.
Hello?
Hello. Hey, William, do you know where saturated liquid is?
Are we talking about in the diagram?
Yeah, where is it on the diagram?
Is it not on the left-hand side of the
Yes,
vapor dome?
yes. You know exactly where it is. It's right here. Here's state 2 right here. It's called saturated liquid. That's what they said we got. We got saturated liquid at state 2. Okay, well, let's get the info on that. We need V2, T2. Now, you know what? T2 is the same, guys. T2 is 4581 because it's on the same isotherm, see it? But V2 and H2 we need. Now, I'm going to shut up for a minute, maybe a minute and a half. But I bet you can do this. I want you to get, I'm going to call on one of you excellent students. I want to know what V2 is and what H2 is. Okay, I'm shutting up now. Find it. Well, let me go to somebody here. Nathan, unmute and say hello, please.
Hello.
Nathan, have you figured out what V2 is yet?
Oh, I hope so. So the X value is 0, is that correct?
That is correct.
Okay, so it's just for V2, it's just 0.00101.
You got it.
And then H2 then would be 191.81.
You got it. You didn't even have to look anything up. It's right there on the board. Good going. Now here's something I forgot. This is a process. There's state 1, there's state 2. You're supposed to draw the process. Look, there it is. I'm drawing the process. I'm going to put an arrowhead on it. I got a 1, I got a 2, I got my process, I got an arrowhead. That is your process from 1 to 2. Now we've got to do from 3 to 4. Okay. Well, now this is lake water, they said. So I would say the pressure would be atmospheric pressure, right? What is atmospheric pressure? It's around 100 kilopascals. The standard atmospheric pressure is sort of an average, is a 101 point blah blah something. But 100 kilopascals is good enough for me. It actually varies. You know that. Atmospheric pressure, you have high pressure sometimes, and you have low pressure sometimes. But it all averages out to around 100 kilopascals. Well, you know what? 100 kilopascals, that's bigger than 10. 100's bigger than 10. So I don't know, we're up in here someplace, okay? There's 100 kilopascals. And now what do we know about the temperature? Well, coming in, it's 20 degrees. Well, where is 20 degrees? Well, you know what? 20 is, it's colder than 45, isn't it? 20 is colder than 45. So I'm going to fake it here and put a 20-degree isotherm in here. Here goes. Now that right there, I just drew a 20-degree Celsius isotherm. Now this one here is the 45.81 degrees Celsius isotherm. Now what do we know about state 3? Well, we know it's 20 degrees Celsius and around 100 kilopascals. Hey, there's state 3 right there. Do you see it? There's state 3 right there. Well, we need some info on there. Do I have any room here? Let's see. There's a little room right in here. Now what I want is I want V3. I don't need T3 because I know T3. T3 is 20 degrees Celsius. I already got that. But I might need H3. See, I might need those for the first law of thermodynamics that we're going to use here in a little while. But how would you get V3? Well, I guess you could go to, I was going to say go to the compressed liquid, but you're not going to find it there because the pressure's not high enough. I think it starts at 5,000 kilopascals. But see, these isotherms basically go straight up. So whatever the V is here is the same V that you have there. And I'll tell you, what I'm trying to tell you is that V3 will equal the VF for 20 degrees Celsius. Well, what is that VF for 20 degrees Celsius? It's 0.001017. Let me write that down. 0.001017. Now, you notice it's a little bigger. I'm getting mixed up now. I was doing fine. Yeah. See this V2 here? It's 0.00101. Okay, now I'm thoroughly mixed up. Just a second now. Let me get my mind right. We're trying to do the lake water now.
For the 20 degrees Celsius isotherm,
Yeah.
so for that VF, are you getting that from the saturated water table?
Yes, I am. Yes, did I
I'm
get the
getting-
right one? Let me look again here.
No, I'm
What
getting
I want is 20 degrees, 0.001017. Yeah, I think I did that right. Yeah. Now, who am I talking to?
This is Bryce. I'm showing I'm showing a 0.001002, but I don't know why I'm showing that.
At
So was mine.
Table B12.
at 20 degrees Celsius, I'm getting 0.001017.
Wait. Okay. That's because you're at 20 kPa.
Oh, no, I see my problem. Bryce, I was wrong. I'm going to give Bryce a big honking thank you point. I was on the wrong table. This is wrong. It's 0.001002, just like Bryce was trying to tell me. He was being so polite about it. Thank you, Bryce. But I think we've got our V3 now. And see this V2 is 0.001010, and 10's bigger than 2. And so it didn't compute before, but it does now. Everything's okay. Now we need H3. Now to get H3, you just, well, H3 is approximately equal to HF, but I'll show you a better way. HF at 20 degrees, let me see if I can find that. That is equal to 8394. Hey, Bryce, do you see that 8394?
Yes, sir.
Good going. Actually, the correct way to do that, let's see, I got a little room right here. Let me make it, show you right here. H3 is really going to be, well, you know the equation. It's U plus PV. Isn't that the definition of specific enthalpy? See, big H is big U plus P big V. Little h is little u plus P little v. This will be a slightly different, but it's hardly worth doing, but I'm going to show it to you anyway. Now the u's are the same. The u will be the u at 20, which is 8394. Let me write that down. This is 8394. And see, the pressure is 100 kilopascals. And the V, we just did the V. It's, oh gee, I don't want to run into that. It's the 0.001002. Okay, now if you'll do that with me, we'll get a slightly better value, but you'll see it doesn't make much difference. 83.94 plus 100 times 0.001002 gives you H3 is 84.04. You guys read that? This is slightly better. I'm going to keep that one. This is off a little bit. I'm going to put a little happy face on this one. This one's off just a little bit. But in a pinch, you can use it. But enthalpy changes with the pressure. See, enthalpy depends not only on you, but it depends on the pressure. So it makes a slight difference, not much. What is the difference between those two? Not much. And 0.1 maybe? If you add 0.1 to that, I think you get that. 0.1 kilojoule per kilogram. Okay, guys, we've done all of our groundwork here. We've got our device sketch. We've labeled it with temperatures and pressures. And we found our specific volumes and our specific entropies. No. We haven't learned about entropy yet. Specific enthalpies. We've drawn our, hey, wait a minute, Auga, we haven't drawn our process from 3 to 4 yet. Now remember, heat exchangers are isobaric, and we're going to go from 20 to 30 degrees. Now let's draw our 30-degree isotherm. Here goes. See, this was the 20-degree isotherm. Now here comes the 30-degree isotherm. It's not supposed to close in on the other one. It kind of goes through there like that. See, this is your 30-degree isotherm. And this is your 20-degree isotherm. And we know that we're at 30 degrees and 100 kilopascals. So here's state 4. And here's our process. Here it is. It's a little tiny one, isn't it? You're going to go from 3 to 4 on that isobar at constant pressure of 100 kilopascals, and we're going to go from 20 to 30 degrees Celsius. So we have 2 processes on one PV diagram. We've done what we always do. We've done our device sketch, PV diagram, put our processes on there.
Professor Griffin.
Yes, I'm listening.
So we're going from 1 to 2, and we're going from 3 to 4, but are we
Yes.
going from 2 to 3? I know that they're 2. I know we're talking about.
No, they're totally separate.
Okay.
This piping here is totally separate.
Okay. So why do they label it 3 and 4 and not like 1A and 1B, 1A and 2A or something like that? Like it seems like it should be going
When
from
you go A and B or alpha and beta or whatever you want. But see, what we got here is a box with no heat transfer to the outside. The Q here is 0 to the environment. But I'll tell you what's going to happen. See, the temperature coming in here is 45 degrees Celsius. That's pretty hot. If you had a temperature of 45 degrees Celsius, you'd be dead, wouldn't you? Isn't body temperature something like 32 or something like that? But see, you're coming in here at 45 Celsius, and you're actually going out at 45 Celsius. So you're not changing your temperature any, but you're condensing. This thing is a type of heat exchanger called a condenser. There's different kinds. Now, condensing is the opposite of boiling or evaporation. If you were to go to the right, if you went from here over to here, they call that boiling. And you know what? It takes energy to boil. You got to turn on the stove. Go down, go to your kitchen, put some water on, turn on the fire, and after a while, you can boil some water. You have to input heat energy to your water to boil it. But see, this is the opposite. You're not inputting heat energy. You're giving off energy. This water coming in gives energy to the cooling water. Here, I'll draw you a heat transfer inside here, if this makes any sense. See, inside here, you have a Q, all right, but it's going to the piping, to the water in the piping. See, the water comes in at 20, and it encounters this 45-degree water, and it warms up, and by the time it goes through all these, it's like a radiator. It's the opposite of a radiator. See, a radiator is supposed to keep your water cool, but this one's warming up, and you're coming out at 30. You go in at 20, come out at 30. How come? Because you got 45-degree water flowing over your coils. Now, who was I just talking to? Who was that?
This is Dawson.
Dawson?
Yes.
Dawson, did I explain that to where you understand it now?
Yeah, it makes sense. It just looks like whenever you're drawing it on a PV diagram or whenever you're doing it, it just looks like 1 to 2, and then it just seems like you would go from 2 to 3. But I understand that it's two completely separate processes.
Oh, yeah, Dawson, totally separate. Totally separate.
I still have a question about the condensers. What we gain by condensing the I'm sorry, was this refrigerant or water?
It's water in this case, Taylor.
So if our water comes out the same temperature it was before, but it's more condensed, what is that? How do we use that?
Do not think of condensing as scrunching something down and making it smaller. We're not doing that. We're changing from vapor to liquid. See, over on this side, this is mostly vapor. Over on this side, this is mostly liquid. The name for that is condensing. When you go from a vapor to a liquid, they call it condensing. It's the mechanism that causes hurricanes, actually, Taylor. See, in a storm, when the vapor condenses and turns into rain, it gives off energy, heat energy. Condensing gives off energy. See, boiling requires energy. That makes sense. You know that to boil, it requires energy. But see,
Right.
Condensing gives off energy. It's the mechanism of thunderstorms. That condensing water into water droplets from a vapor gives off energy, and that warms up the air and it makes it rise. And as it rises, it cools off, you get more condensing, and pretty soon you've got yourself a storm. A hurricane's the same thing. The energy from hurricanes comes from condensing. Now, not only from going from vapor to a liquid, but going from a liquid to a solid. See, in a good thunderstorm, you get hail. You know that. You've seen in Oklahoma, you've seen hail before. Well, see, when you go from a liquid to a solid, they call that freezing. And the crazy thing is, when water freezes, it gives off energy. That's counterintuitive. And that energy is really the energy of that thunderstorm. See, as you're creating hail, you're giving off energy, and that powers your thunderstorm. To explain it, to go the other way, to go from solid ice to liquid water, they call that melting. Did you know requires a heat transfer in. I tell you what'll work. Take a piece of ice, put it in your hand, and you can melt that ice. And you know why? Because there's a heat transfer from your warm hand to that ice, and it turns into water. They call it melting. But see, when you go the other way, when the water goes from liquid to ice, it gives off heat. Did that make a lick of sense to anybody?
That makes sense to me. But looking at it from less of a natural standpoint and more of a like a refrigerator uses a condenser, right?
Yes.
So how does the condenser help keep things cool, I guess, is what I'm
Well,
asking.
now wait a minute. Now I'm getting mixed up.
Or why does a refrigerator have a condenser?
Yeah, a refrigerator has a condenser. That is true. And it has an evaporator too. A condenser and evaporator. And we're going to study the refrigeration cycle. We're going to study refrigeration cycle. But see, what you're really interested in with the refrigerator is that transfer from liquid to solid. You know, you're freezing, and you have to remove heat from that. It's sort of like it's sort of like evaporation, only they call it sublimation. When you go from a solid to a vapor, they call that sublimation. Anyway, you're getting Taylor, you're getting me all mixed up. I need to finish this problem here.
Okay, thank you.
You are asking some wonderful questions. What we got to do now is the first law of thermodynamics. So I need the room. We got all our info here. I just need the room to write it. Is there enough room? I think so. Now, the first law of thermodynamics we all know and love. It goes like this. This is a simplified version because we don't need to worry about I don't know what I was going to say. I had a senior moment, but the thing is, go ahead.
I think the problem, you're right. The problem mentioned something about energies being minuscule, or you didn't have to worry about them.
Yeah, that's it. Thank you. Yeah, we don't need to worry about kinetic energies. Nothing's going fast enough to worry about, or potential energies. But here's what's different about this one. We've got two inputs. We have the cooling water, and that would be H3 minus H4. But see, we have two of these terms. We have the what do they call this? The water coming in at 45. I don't know what to call it. Just call it H2O. There you go. And this will be H1 minus H2. Now, I've already done some algebra on this. And for the whole thing, guys, this is zero. Remember, that's the heat transfer with your environment. That's zero. And here's something else I forgot to tell you. Heat exchangers, they don't have any power. You don't have to plug them in. All you got to do is put the flow going in and the flow going out, put the piping in. And this is zero because it's steady state. So nothing's changing with time. This thing will just run like this for hours, okay? There's no heat exchange with the environment. There's no power requirement. But we have two terms here. We have two different inputs. Now we don't know does that show up over there? Yeah, let's put it over here. We don't know the cooling water flow rate, but we do know what H3 is. It's 8404, see it? 8404 kilojoules per kilogram. And that's H3. And we know H4 too, someplace. Well, where is it? Did we ever get H4?
I don't think so.
I don't think we did. But I tell you how we can get it. The same process that we did before. We can go to 30 degrees. And we can, let me do it down here. H4 is going to be U4 plus P4V4. Well, U4 is, and we're talking about 30 degrees now. See, state 4 is at 30 degrees. And so U4 is, let me find it here, 125.77. And the pressure there is 100 kilopascals. And the V at 4, we do have the V at 4, don't we? I guess not. I don't see it. But I can easily get it. It's right here. At 30 degrees, the V at 4 is 0.01. No. 0.001. 004. Yeah, that's it. So I can get the H4, and I'm going to put it right here. Here goes. There's really an easier way to do that. Well, if I did that right, I'm getting 125, and I hope somebody's checking me here. 125.87. Okay, now I've got 0 equals 0 minus 0 plus this, plus, they gave us this. They said this is 1 kilogram per second. So that's a 1 kilogram per second. Now H1 and H2, we got those. H1, or do we? Yeah, here we are. Here's H1. I need that room. We're going to have to sacrifice here. H1 is 2464. $99. And H2 is, we're doing this equation, we're plugging in H2, where'd it go? There it is, 191.81. Hey, we can solve all that, and we can get our mass flow rate of the cooling water. Now, I've got an answer book here someplace. Let me dig it up. You guys do that for me. We'll take a minute out, plug all that stuff in, and solve for the mass flow rate of the cooling water. And I'm going to go get my answer book, and we'll check it. We'll see how we did. Okay, I've got my answer book. We're doing problem 459. Pretty sure I've got that here. Let's see. Yeah. Okay. Let me call on one of my excellent students. We're solving for the mass flow rate of the cooling water. And we're going to go to my friend, let's see. How about Alex? Alex, unmute and say hello, Alex.
Hello.
Hey, Alex, did you solve this equation right here? It's kind of ugly. And get the mass flow rate of the cooling water.
I got 3.99. Is that what you got?
Well, that's not what the answer book says.
Let me try it again.
Maybe they're wrong. Let me try it. That's not what they said there. Try it again. And I'm going to try it too. That is, if I can find my calculator. Dang it.
Oh, I'm getting something different. Is it 55.34?
Hey, I like that better.
That sounds
I
better.
like that better. I like that a lot better. I don't know what I did with my calculator. Dang it. Hang on. Let me shove. Yeah, here it is. That's still not exactly what they got, but I like it a lot better. Okay. I see that they have they did it a slightly different way. They got pretty much everything that we have, only they said that this here is 83.94. Oh, I see what they did. They were lazy. Do you remember I told you that the 8394 is dang close. Put a little squiggle there. And the 8404 is slightly better. The answer book used 8404. No. The answer book used 8394 right here. And their answer is slightly different than ours. But Alex, what did you get?
I got 54.34.
54.34. And I believe that is correct. You got 54.34?
Correct.
Well, that's what they got. But see, if you use this 8404, you get a slightly different answer. Let me do it. Hang on. Okay, 8404 minus 125.87. Of course, that's minus, but if you do a little algebra, it becomes positive on the other side. And then you divide by 2464.99 minus 191.81. And something bad happened. Oh, I think I did it the wrong way. It's 54.34. It's 54.34. And well, that's what the answer book says. The answer book says 54.3 kilograms per second. So we just did a a heat exchanger problem. Any comments or questions on that? Well, I have one more topic here today, and we have time to do it. I'm going to erase all this unless somebody has a question. Unless you have a question. Okay. Say goodbye to the heat exchanger. Okay. We know there's different versions of the first law of thermodynamics. When we started off in this course, we did a first law for controlled masses. And it went like this. Ta-da. And for practical purposes, you can usually get away with using that there because you can assume you don't need to worry about kinetic and potential terms. And then we did the first law for controlled volume. And you know how that goes. That's what we've been using in this chapter. Getting a little lazy there. We still haven't used that with things that you need these for. I take that back. You need that velocity term for your nozzles. Now, if you had a pipeline that was pumping water up a mountain, you would need the gravitational terms. And this one is the first law for controlled volumes, but there's another first law for transients, transient processes. Now, there's a section in your chapter about it. Let me show you where it is here. See if I can find it here. Transient problems. What that is when you start up a turbine, for instance, this is on page 131. When you start up a turbine, it's not steady state because when you start it up, it doesn't have any steam in it. The rotors aren't turning. They start increasing velocity, pressure builds up. It's not steady state, it's changing with time. Also, when you shut down a device like a turbine, you shut it down, they have to do that occasionally to make repairs. And they call that a transient process. It's a process where things change with time. And the first law looks like this. It's a little bit nasty. This is in your book. It's all on page 132. Now, what these terms are, those are the initial and final energies, is what they are. Internal energies, kinetic and potential energies. This is the final, this is the initial. There's no dots on these because there's no dots on these. No dots on this one either. Uh-oh. I'm running out of room here. We'll squeeze it in here somehow. I'll just get lazy and go like that. This is a pretty hairy looking thing. It's pretty long and hairy. There it goes. That's the first law for transient problems. Now we've got 11 minutes. I got time to do one. We'll do a simple one. And this one happens to be problem 464. We're going to do problem 464, but you need to know that there's different forms of the first law. There's your first law that we studied back in August, I guess, right? This is October. And there's your first law that we've been studying here lately, this past few meetings. But there's also the transient form when things are not steady state. And this problem is 464. And if you do the device sketch, here's what you've got. You've got an empty container with a line coming in. Let me find it here. Oh, gee, I'm going to have to hurry. I only have 10 minutes, but this is pretty interesting. If I can find it, 464. There it is. Is that the one I want? That's not the one I want. Sorry, that's not the one I want. I can't read my own, it's 484, sorry. Can't read my own writing. But if you'll find 484, it says, there we go. Insulated 2 cubic meter tank. This is 2 cubic meters. Here is state 1. And later, we'll draw it here. There's a line coming in here. The line has R134A in it. And it's at 3 megapascals, 90 degrees Celsius. And there's a valve here. This is empty. This starts off empty. And then somebody opens the valve. And this R134A starts to come in there and fill this thing up. And if you read the problem 484, it fills it up until it's got 3 megapascals. See, right now it's got 0 megapascals because it's empty. And then if you run a line here with 3 megapascals at 90 degrees Celsius, it eventually will fill up to 3 megapascals. That kind of makes sense. They want to know what the mass is and the temperature. They want to know what M2 is, and they'd like to know what T2 is. Okay. Well, we need to draw the PV diagram, and then we'll use this as our first law, because it's a transient problem. See, stuff is changing with time. Okay, well, let's draw the PV diagram. Here we go. PV diagram. Now, state 1 has 0 megapascals. That must mean that state 1 is along this line here. That's 0, isn't it? And if there's nothing in there, that means the mass is 0. Well, mass is equal to the volume divided by the specific volume. And if the mass is 0 and the volume is 2 cubic meters, well, then the specific volume must be very large. You're way the heck over here someplace, you understand? And what happens is, as you open this valve, the pressure starts increasing. It will increase until you reach 3 megapascals. It starts way the heck over here, comes up here. Here's state 1, here's state 2. There's your process. Okay, now this stuff here is at 3 megapascals and 90 degrees C. Well, I don't know where 90 degrees is exactly, but those of you that have dealt with filling tanks like this know that these get very hot. This is going to be hotter than 90. See, this stuff is coming in at 90, but it's going to be hotter than 90. So how would I draw that? And well, we'll try. Here's 90. Well, where's my PV diagram? We're entirely vapor here. Yeah, we're entirely vapor. Yeah, there you go. And what is the temperature is 90. What is the oh gosh, I'm running out of time. Help me find the R134A in the back. I'm trying to find it, the R134A. Aha, I got it. Now, this stuff coming in is at 3 megapascals. All right, it's kind of up there around 85, 90 degrees. 134A, 3 megapascals, 90 degrees. All right. Well, let me draw that 90 degrees. So, this right here is somewhere around 85, 90 degrees. It's actually about 87 degrees, something like that. But see, we're going to be at 90 degrees. So that puts us right about here. 3 megapascals, 90 degrees. But our pressure is going to be 3 megapascals. But here's going to be state 2. Now, I don't know what that temperature is, but I have a feeling it's a lot hotter than 90 degrees. This is T2, and we can get it. And here's your incoming state, and here's your final state 2. Here's your incoming state at 90. See, 90, we can draw 90. It's just like this. There's 90. You're coming in at 90, and you're going out much hotter. Okay, now let's write our equation. I got 2 minutes. I think I got time to write our equation. You guys could solve it. We can throw out that term and that term. We don't need to worry about the velocities. And you know what? We can throw out this entire term. How come? Why can we throw out that entire state 1 term? Why is that? Let me ask somebody. Braxton, unmute and say hello, please.
Hello.
Braxton, why are we able to throw out this entire state one term? How come?
Because it has no mass. So
It's
mass is
got
0.
no mass. It's empty. It's empty. So this whole thing over here on the left is M2U2. Now over here on the right, this here is 0. There's no heat exchange with the environment yet. Now there will be, because it's going to get hot and it will radiate heat out to the environment. But this happens pretty fast. You open that valve, it fills up, it gets pistol hot. It doesn't do any work. When you open the valve, you don't do any work. And what you have left over here is MIHI. You don't need to worry about these terms here. And you certainly don't, Braxton, you don't need to worry about this term here. This is the exiting term. Braxton, tell the group why there's no exiting term needed here. Why is that? See, this is the incoming term. Stuff's coming in, but we don't need an exiting term. Why is that, Braxton?
Oh, because nothing's exiting. Yeah.
Nothing is
Okay.
exiting. Nothing is exiting. Stuff's coming in, but nothing is going out. And hey, this simplifies to a very simple equation. And in fact, can you see that the final mass is going to equal the incoming mass? Now, do they tell you how much the incoming mass is? Oh gosh, I'm going to run out of time. What do we got here? 484. Let me see it. Charge of the line flowing. Valve closed, pressure inside. Oh, here we go. Well, now how are we going to get that mass? We know the volume. Yeah. Valve is closed, pressure inside.
Specific volume of R134A at those conditions.
Yeah, that's the way you got to do it. The mass is equal to the volume divided by the specific volume. They give you the volume, it's 2 cubic meters. And the specific volume coming in, we can look up. We don't have time, but we could look it up and you could get the mass. But whatever the mass is coming in, that's the mass that you got to end with. And so this equation boils down to a very simple equation, U2 equals HI. And you can look up HI in the tables, get U2 from the tables, because we know the final pressure and you can get the temperature, but we're out of time. But I got you started on it. I gave you a few hints there about transient processes. Any last words? We're going to say goodbye.
Yes, Mr.
Any
Good.
last words? You got your homework.
I have a
I
question.
guess there's a test next week.
I have a
Question.
question.
Okay. Anything?
Yes, I have a
All
question.
right. Well, yeah, go ahead.
When are you going to post the test?
It will be available next Thursday. I think, isn't that what I said? And then it's due on Sunday?
Yeah, it's due on Sunday. Yeah.
Yeah, it's available Thursday, due on Sunday. Thank you for asking. Okay, bye-bye for now, students. See you next Tuesday at 11, right?
Sir,
Okay, enjoy.
have a good weekend.